Hey everyone, welcome back to week 14. So I just finished the exercises at the end of chapter 3, and today I want to talk about exercise 3.13, which is about KL divergence. So let's do it. All right, so what is the KL divergence? So first we let d subscript KL be defined as this function here. So it's just a function, and it looks like this. Okay, you take some vectors u and v with the same size, and they must be, strictly positive vectors. Then you take the sum of the ith entry of u, log of the ith entry of u over v minus u of I plus v of I. And you take the sum of all our entries in each vector. Okay, and then what we want to do is we want to prove that this function is greater than or equal to 0 for all u and v in the positive vector space. Okay. The second thing we want to prove is that this function is equal to 0 if and only if u is equal to v. If you've taken any ML course, you've probably seen this stated as a fact. It's used to justify cross-entropy loss, and it shows up in a lot of places, but you've most likely never seen it proved. So that's what we're going to do today. The problem also comes with a hint, and the hint really is kind of the whole key here. So the hint says that the KL divergence can be written as this function here. These are equivalent definitions, where F is the negative entropy of V. So based on all this so far, we sort of get a feeling on how we would solve this problem, right? The strategy we're pointed towards is we want to express KL divergence as something we already know, which is non-negative from convexity theory. So let's do that. Before the proof, I want to say one quick note about the definition. The formula Boyd uses with those extra UIs and VI terms is the generalized KL divergence. So it works for any positive U and V, right? U and V could be any positive n-dimensional vector. However, if U and V happen to sum to 1, as seen here, then they're probability distributions, right? So those extra terms cancel out, these UIs and VIs here, because they all sum to 1, so they must cancel. And you get back the form you've seen in machine learning, which is this expression here. This might be the familiar expression to you. But the generalized version is what we need, so the proof works cleanly for all positive vectors. Okay, so now let's look at the function more closely in the hint. Okay, first what we do is we just define some function f, which is the negative cross entropy here. So the hint is essentially asking us to use this as our convex function. So first, let's check if this is actually a convex function. So to check if it's a convex function, we have to look at the second derivative, or the Hessian. So starting out with the first derivative, we can see, taking with respect to v, we have log of v plus 1. And then differentiating one more time, we see that the Hessian is a diagonal matrix, with entries 1 over vi. And since vi was positive, we know that this is strictly convex, not just convex, because these terms can't be 0. So here's the key idea. Because f is convex and differentiable, the first order condition holds. So I'm going to remind you what that is as follows. So the first order condition says that for a convex differential f, which f is in this case, then f of u, is greater than or equal to this expression, is the same thing as this, which is rearranged. Which, if you notice, this is exactly the expression on the KL divergence. So now let's verify that this expression is exactly the KL divergence. So just doing some algebra here, we can see, I'm not going to go through every detail, but you can see that this term is indeed equal to the KL divergence. So therefore, since we know that from the first order condition, this expression is greater than or equal to 0, and this expression is equal to the KL divergence, we must conclude that the KL divergence is also greater than or equal to 0. So that proves the first part of the problem. All right, so moving on to part two. Part two is asking us to show that the KL divergence is equal to 0 if and only if the vectors u and v are equal to each other. However, the proof is very straightforward. So because we've showed that f is not only convex, but strictly convex, from here, because f is strictly convex, by definition, the first order condition holds with equality if and only if the 2 points are the same. So, this is kind of a trivial application of the first order condition, when f is strictly convex. So we get this result immediately after we've shown up here that f was strictly convex. So now we've shown 1 and 2 is true. So let's look at the geometry now. So hopefully, because we've drawn parallels with the convex definition earlier, we should see a similar, geometric picture. And indeed we do. So the KL divergence can be interpreted as the gap between f of u and its tangent plane at v. So convexity guarantees that the gap is non-negative. Strict convexity says the gap is 0 only when u equals v. So for example, a strict convex function will never be a straight line. Then it would be overlapping with the tangent plane everywhere. And this picture generalizes too. Any strictly convex function f gives you a divergence this way. It's called the Bregman divergence, if you're interested. KL is a specific one you get from negative entropy. So every time you use a cross-entropy loss, you're minimizing a KL divergence. The fact that KL is greater than or equal to 0 with equality only at the right answer is what makes it a valid loss, and the entire justification in this proof. All right, so that was 3.13. It was clean, but informative. Past week was pretty difficult for me because there are many tough problems, but I'm still grinding away and learning a bunch. So I'm also very excited to start chapter 4 next week. So I'll see you then.